Hello everybody and welcome to the Kinetic Energy video of our work energy and power unit. Hopefully you just watched the potential energy. These two kind of go together nicely, and tomorrow we will look at conservation of energy, which brings these two together. So anyways, let's dive into kinetic energy. Kinetic energy is the energy of motion. So you'll see in the formula that it depends on velocity, so the kinetic energy is always moving energy or energy of motion. So the formula for kinetic energy is EK, so energy kinetic is equal to 1/2 mv squared, where this is our, let's make this a little smaller, kinetic energy in joules, that's just a 1/2. This is mass in kilograms, and this is velocity, and we know velocity is meters per second. Okay, so let's use this formula. Before I dive in, so as long as you know the mass and the velocity of something, you can find its kinetic energy, which is pretty cool. So I guess like we could say that you know what, I'm not even going to make extra problems. Let's just do the ones I've got already ready to go. Example 1, the kinetic energy of a 2.1 kilogram rotten tomato is 1,000 joules. How fast is it moving? So just please remember that I didn't make these problems up, but what I am assuming is happening here is someone's throwing the tomato. I don't really know, but we know mass is 2.1 kilograms. We know kinetic energy is 1,000 joules, and we're trying to find velocity. So let's choose our formula, which is going to be our kinetic energy formula, and let's manipulate. So the first thing we can do is multiply both sides by 2, because 2 over 2 will cancel. I have 2 multiplied by kinetic energy is equal to mass times velocity squared. Divide both sides by mass. That will cancel. I'll flip this around. So I have v squared is equal to 2 multiplied by kinetic energy over the mass. And the last thing I want to do is square root everything. So now I have velocity is equal to 2 multiplied by the kinetic energy divided by the mass, all under the square root. So let's plug that in. Velocity is equal to 2 multiplied by 1,000. Thousands are kinetic energy divided by 2.1. Well, let's do everything under the square root first. So we will have 2,000 up here divided by 2.1, which gives me 952.3. So I can square root that. And we have a velocity of 30.9 meters per second. So that's a pretty fast moving tomato. If it hits you, it's probably going to hurt. So earlier when we looked at force, we talked about the work energy theorem. So let's dive a little bit into that. So basically it says if a net force acts on an object, it must be accelerating. We know that, right? If there's a net force, there's an acceleration. F net is equal to ma. But this must be proportional to its change in kinetic energy. Therefore, we can come up with this formula where work is equal to the change in kinetic energy, which is equal to the F net multiplied by the displacement. So it's kind of this part here that we want to use. So this is the work energy theorem, that the F net multiplied by the displacement is equal to the change in kinetic energy, or vice versa. I think you see this on your formula sheet as this. Work is equal to change in energy, and then it's up to you to kind of put it into that form. All right. Example 2. A sprinter exerts a net force of 260 newtons over a distance of 35 meters. What is his change in kinetic energy? Change in kinetic energy is equal to F net multiplied by displacement. So this one's nice and easy. We know the F net is, they told us right here, 260 newtons multiplied by the displacement, which is 35 meters. And we get, again, I'm going to not trust my answer key. It's always a good idea to do your own calculations. 9,100 joules. All right, let's go to a trickier one. A student pushes a 25 kilogram crate, which is initially at rest, with a force of 160 newtons over a distance of 15 meters. If there's 75 newtons of friction, what is the final speed of the crate? Okay, a couple things we want to look at. We have a crate being pushed with an applied force of 160 newtons and a friction force of 75 newtons. So my net force is going to be 160 plus negative 75. So my net force is going to be 85 newtons. Perfect. The distance is 15 meters, and we know the mass is 25 kilograms. So we are going to use the formula. Change in kinetic energy is equal to F net multiplied by displacement. Anytime we have a change, do you remember this from kinematics? Anytime we have a change, it is final minus initial. So energy kinetic final minus energy kinetic initial will equal F net multiplied by displacement. So let's talk about the kinetic energy initially, right? Because if we can go the extra step and say, well, EK final is going to be 1/2 mv final squared minus EK initial is going to be 1/2 mv initial squared. And that will equal F net multiplied by displacement. So initially, is there any velocity? Does this crate have any velocity? And it says here, a student pushes a 25 kilogram crate, which is initially at rest. So if it's initially at rest, that means VI is equal to 0. And if VI is equal to 0, that means its initial kinetic energy was 0. So this whole term is 0. So now our formula is 1/2 mv final squared is equal to F net multiplied by displacement. And we are trying to solve for the final velocity, so we can do that. Multiply both sides by 2. So that cancels out. And I have mvf squared is equal to 2 multiplied by F net multiplied by displacement. And then I can divide by m to both sides. So now I have Vf squared is equal to 2 multiplied by F net multiplied by displacement all over the mass. And then obviously my last step here is to square root. So I have V final is equal to 2, the square root of 2 multiplied by my net force multiplied by my displacement all over my mass. Let's plug some things in. 2 multiplied by my net force was 85 multiplied by 15 all over my mass of 25. So if I do some of that, let's just leave it like that. We have 2 multiplied by 85 multiplied by 15 divided by 25. So we get the square root of 102. And when we square root that, we are going to get 10.1 liters per second. There you go. That is a little bit of how to use the work energy theorem and a little bit of kinetic energy, which is the energy of motion. So if there's no motion or no velocity, then there's no kinetic energy. Things are going to get really fun with conservation of energy in the next video, and I'm excited to do that one. So I'll stop here, and I will see you all tomorrow. So thank you for watching, and have a good day.